Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so thank you all for attending. It's a small crowd, so really do feel free to interrupt, ask any questions, or offer comments. So I will talk about work which has actually been ongoing for quite a few years, a certain direction, although as you will see from the number and dates of the papers, not at a very fast pace. This work all of it was done with Margarita, Osadchy, a former graduate student of mine who was back at Haifa University. I say because we are a really small university and a really tiny department, people often say, oh, you're from the Technion. So we're definitely not from the Technion, and they will be very insulted if they hear you making this assumption. We are about half a mile from the Technion. Like I said, relatively small, a new department, just 15 faculty. But 3 of us are in computer vision, so in that regard, we are leaders. So this is work which some of it was presented at last ECCV in Florence. And what we want to do is we want to do image classification. And the basic problem is that you have a positive class, which is usually very small, and a negative class, which is huge. All of you must know, of course, is databases with, I don't know, it's up to 10,000 categories or something. And in this particular work, we are interested only in a classification of one category versus the rest. Okay? Not necessarily identifying the class itself, but just looking at it as the most basic question. You have an image, and you have to say whether it's an image of a bicycle or not. Okay? So it's, of course, a very, very, very unbalanced problem. Okay? You usually have a very small positive training set. Typically, it's, I think, about 30 or 40 images, right? These are the numbers. Versus tens of thousands of images, or maybe hundreds of thousands. If you have 10,000 categories, and so your negative class can be up to a few hundreds of thousands images. There are many solutions. I cannot do justice to all of them and go through all of them carefully. There's weighted SVM, which tries to balance this big difference in the size of the classes by giving a higher weight to the positive samples. And of course, you can do undersampling of the huge class and oversampling of the small class, for example, by artificially creating more examples from the small class. But these methods are always run into computational problems. There has been a lot of great work done on solving the computational difficulty involved in training SVM with a very high number of samples. So first of all, you can do linear SVM, which is still difficult, but more computationally tractable and does reasonably good work. And then you have all these really heavy machinery, which I don't know if anybody else understands except these guys, which come from the machine learning part, Joran Zinger and many other people. So you have the linear methods, you have the kernel approximations, which trade accuracy for complexity, and you have all kinds of kernels, which are not the most general, but can still do a good job in certain cases. Okay, but the kernel there has to satisfy some constraints in order for you to be able to apply these methods. And in exactly the same conference in which we presented this work, there was a paper which is the most similar to what we do. This paper, which is a very nice piece of work by Keren and Malik and Deva. And it resembles our work because they also use a prior on the negative examples. And this is the heart of what I'm going to talk about, and it's a very straightforward idea. And it works reasonably well, actually better than what we expected. So let me go directly into the details. So you have a positive class, for example, cars, and the negative class is the rest. Now, the rest is all non-cars. But basically, all non-cars is all non-dogs and all non... I mean, they're all almost the same. If you look at all the images which are non-cars and non-cats, they're almost exactly the same, of course. There's like, I don't know, maybe 0.1% difference between these classes, right? And it's basically all natural images, okay? So we like to think of this problem as not separating one category from the other, but separating a category from all natural images, whatever that may be. Okay, and this is just, I mean, you all know how this looks. You have this huge background consisting of many, many categories. It's very, very complicated. Okay, I want to really briefly talk about very old work. This was the basis of Rita's PhD. And there we faced exactly the same problem, but it was much simpler. We did it only for gray levels. And the question was exactly the same, okay? You have, for example, some images of somebody's face, and you want to separate them from everything else. So here is the same theme, which will be all over this talk, is that your background, your negative class, is huge. It's basically everything. So there was a very simple solution, which worked well. Of course, in terms of performance, it does really much less than today's results. So what we did is the following. I will soon show you a plot with some nice images, but just to explain the idea. So natural images, as we all know, are smooth. Remember, this is very simple. This is not any high-level features. This work was done on the gray levels themselves. And as we all know, natural images are very, very smooth, much, much smoother than a random vector. We all know this. You look at the Fourier coefficients, and they're all concentrated in the low frequencies, etc. Then there was an observation that if you take two smooth vectors and you multiply them, you compute the inner product, you get a very large number, an absolute value, of course. It's much larger than the product of two random vectors. I could prove that to you, but I don't have the time, but you probably believe me because it does make sense, right? And then what we do is the following. We created what we call antifaces. We call them antifaces because these detectors, or rejectors, as we call them, are actually orthogonal to the images we're looking for. So suppose that you have something which is orthogonal to the class which you want to detect, but also is mostly concentrated in the low frequencies, okay? I mean, it's a nice and smooth image. So if you take that and you multiply it with your images, you'll get a very small result because it's nearly orthogonal to them. But if you multiply it, I mean, compute the inner product, with a random image, but not just random, as in, random numbers, but a random smooth image, you will get a very large number. So you simply accept only the one which have a small inner product with your images, with your positive class. And there was some follow-up on that. So how does it look? It looks like this. This is, like I said, really an old image from the PAMI 2001 paper, I think it was. So suppose you want to identify the images of this lady, ST. This is an example from the paper. So we took many, many images in different rotations and scalings. And these are the anti-ST detectors, okay? By which I mean that all of them satisfy the following property. First of all, as you can see, they are very, very smooth, okay? Second, they're all nearly orthogonal to all the ST images. There were, of course, thousands of images like that of this face. I'm just showing you an example. And another thing you can do is here you have the first one, okay? And then you can create another one. But you demand that the second one will also be orthogonal to the first one, okay? And then you can prove that the operator is independent detectors. And I don't know if you may have seen your Wolf, a recent work also from ECCV 12, in which this idea of having a few orthogonal or independent detectors works in order to enhance your detection. Okay? So what you do, you have like a cascade of rejectors. You look at everything which passed this guy, then you operate this guy, this guy, this guy, and eventually you're only left, I mean, this is just a schematic example, you're only left with the ST images. So this is old work. It was, like I said, applied to gray level images, and it works actually not bad. Okay? It can identify a rather complicated collection of images. It does have a very serious drawback. Its generalization ability is very, very weak. Okay? But at the time, it was good enough to be accepted. Probably not today. Okay, then quite a few years passed by. Rita went, did a postdoc, came back, and we wanted to extend this idea to do something in order to obtain better results, to apply it with a maximal margin classifier. So the idea was really, really simple. This is a paper which was in CVPR in New York, 2006. And the idea was the following. You do something which looks exactly like an SVM classifier, a linear one. But, and here, this is really basically the only idea in this talk and in this work is very simple. Instead of minimizing the number of background, by background I mean, of course, negative samples, instead of minimizing the number of the background samples which you accept, I mean, when I say acceptance region, I just mean, of course, the positive side of the SVM classifier, or the maximal margin classifier. Instead of minimizing that, you minimize the probability volume of the background to be in the acceptance region. Okay? And as I will hopefully convince you, this allows you to replace a numerous number of constraints on the negative samples by one constraint. Okay? So don't work with the samples, work with the probability. That's it. That's the whole idea. It's really, really simple and straightforward. So what's the advantage? No negative samples, far less constraints in the optimization, no negative support vectors, which make life really hard if you're doing kernel SVM. And the background can be modeled just once. This is also a point which is emphasized in the Hariharan et al. Paper, that once you model the background once, you can use it to construct classifiers for all your 1,000 or 2,000 categories. Because you assume that the background is the same, okay, for all categories. Because it's nearly the same, and like I said, the background is just everything. So you model it just once. That's really important from the computational point of view. Questions so far? Good. Okay, so how does it look? It looks very simple. This is a schematic drawing, which probably could have been better. Assume that your prior is that this rectangle represents all natural images. Okay, and assume that the probability, the prior, is higher where the color is darker. Okay, and assume that these are your positive samples. So you look for a hyperplane, which does what? Which, exactly like SVM, which has a wide margin, which puts the positive samples on the right side, okay? And on the other side, it tries to maximize the integral of the prior. Okay? So does this make sense to everybody? Okay. And that's it. So the idea is just to take the SVM, the basic idea of the SVM, but replace the negative samples with a probability. So here's another schematic example. Suppose that this is Z represents the background, and this is assume for the while that it's a Gaussian. And this is your hyperplane. You try to put the positive examples here, but you want to leave as small as possible probability on this side. Okay, so you see that this is like here, if you would compute the integral of the probability over this half plane, over the acceptance region, you would get a small number. That's it. That's the whole idea. Okay? And the question is how to enforce this condition. Okay? Good. So how do we do this? First of all, we have to model the background. And as we all know, modeling the entire distribution of natural images is extremely difficult. There's a lot of work on that. Okay? Some done by Mumford, by Yair Weiss. Many people worked on this, and it's actually an extremely difficult problem. But what we want to claim is that it's not such a big problem when you're dealing with detection, as opposed to synthesizing images, which is really difficult. Okay? When you're doing detection, it's actually not that much of a problem. And why is that? Because how do we classify images? We have a function which collapses everything into the real line. Okay? If it's a linear SVM, we just take an inner product and add some constant, and that's it. So you have this really, really very, very complicated space with a really, really complicated prior, which nobody knows, of course. But you collapse it into one dimension. And then obviously you get a much, much simpler probability structure, right? Which, sort of like a central limit theorem, will typically look like a Gaussian. That's it. So it's much simpler than this very, you just go around this really difficult problem because you're eventually working with one-dimensional data. So either linear or kernel, it doesn't matter. Basically, you collapse everything to the real line, and then you have to model, since eventually the detection is done after the projection, then you have to solve a one-dimensional problem. And that we know how to do. So how does it look? It looks like this. Suppose that you take random vectors, either linear or kernel, and you take many, many, many images, and you compute the value of the kernel, either linear, like I said, or kernel, doesn't matter. Then the distribution of the values looks more or less like a Gaussian. Okay, which is not really surprising. I mean, everything which is really big after you collapse it to the real line looks like a Gaussian, although sometimes it does have a long tail. And we got a lot of comments from the reviewers that why do you use a Gaussian? Why don't you use something more complicated? The answer is we tried, it just didn't work. So we just approximate all the projections on the real line of the background with Gaussians. And it did good enough. I mean, good enough. Good enough for the paper to be accepted. And that's sufficient for the meanwhile. Okay? And there are also theorems. There's a paper by Diaconis from Harvard. And it talks about this paper proves that under certain assumptions, which typically hold, if you take low-dimensional projections of high-dimensional data, not necessarily linear, they can be well approximated by a Gaussian. Okay? So this holds also for kernels, not just for inner products. Okay, so how does the linear hybrid classifier look? We call it hybrid because you model the positive with samples and the negatives with a prior. Okay, that's why we use the name hybrid. So we have to have this condition hold. Okay, this is the condition for the background. But if you assume a Gaussian, you can simply calculate this probability, and you get this expression. It's just a one-dimensional Gaussian integral. It's no big deal. And you have to believe me, I will not bore you with the details. It's really straightforward. Eventually, you get a convex condition. Of course, what I'm swiping under the rug here is the fact that you have to have the average and the covariance of the background. So we simply estimate them. We take 1,000, 2,000, doesn't matter, examples, and we estimate empirically the average and covariance matrix of the background. As I said, from the computational point of view, it's very important. this has to be done only once. If you have 2,000 categories and you want to build a classifier for each, this estimate, which can be costly, is done only once. Okay? Okay. And you get this condition, which is convex. Okay? Now, you may wonder how accurate this estimate is. Okay? Remember that what I'm making a claim here is that the probability, if I choose a random image and compute this probability, that it can be approximated by this ugly thing here. So in order to check it, we did a scatter plot of many, many randomly chosen W's and B's, and computed for each of them the theoretical probability, just this equation, and also the real probability as computed on the background. Okay, so each point here corresponds to a W and a B, and we took, like, I don't know, Rita did all the experiments, like 100,000 images, and calculated for how many of them the condition holds. And as you can see, there is definitely a correlation between the empirical probability and the theoretical one. Actually, the only area of this plot, the scatter plot, which is of interest to us, is this one. Because remember that we want the probability to be very small. Okay? But it turns out to do quite well here. Okay? So how does it look eventually? Eventually, it's a very, very simple optimization problem. Okay? You want to construct your maximal margin classifier using this prio. So you have this condition. This is exactly the same as SVM. This is the wide margin constraint. We demand that these inequalities hold. We can also add the slacks. It doesn't make any real difference. So these two are, of course, familiar to all of you, basic stuff, your SVM. But this condition is the new one, which replaces all the conditions on the negative examples by one single condition. And this condition, as I said, guarantees, depends on the value of gamma, but that's just a constant, guarantees that the probability of a random image to fall in the acceptance region to satisfy this condition will be small. Okay? So your optimization problem is, one, convex. Second, much, much simpler. Assuming, of course, like I said, that you computed these guys, the average of the background and the covariance of the background. But that can be done. Okay? So this is basically it. I will now show you the results, how this works for the kernel, but this is it. So any questions so far? Okay. And so how do you do it for the kernel? For the kernel, it's, of course, trickier. Now, if you think about SVM, as we all know, the SVM classifier gives you a classifier which looks like this, where you forget about this thing, where your SI are, of course, part of the negative and positive samples. But we don't have any negative samples. Okay? So how do we choose these elements, okay, SI, which will define the kernel function we're using? So we a priori decided we're going to use the same equation, the same expression as in kernel SVM. But again, the problem is that the standard SVM, kernel SVM, finds these elements for you. These are just the support vectors. And they are part of your training sample, both positive and negative, but sorry for repeating myself, we don't have the negatives. Now, to restrict the SI to belong only to the positive samples doesn't make any sense, of course. I mean, that's a really, really strong limitation, especially if you have a small number of positive samples. And if you do that, you're not allowing the background to influence the shape of the classifier, which is very bad. Okay? So how do we choose these guys? And after we choose them, the condition is exactly the same. The condition on the background is exactly the same. You remember that you accept vector x if this inequality holds, exactly like in standard kernel SVM. But we want the probability of this, where x is a random variable representing the background, to be as small as possible. Okay? So exactly same idea. Okay. So how do we choose these guys? I will soon talk about that. But first of all, the formalism. And the formalism is exactly the same, right? Okay? You empirically compute the covariance matrix of these, yes, and you see that you get something which is exactly the same form as for the linear case. Okay, so it's a really straightforward process to do. Okay, and exactly the same optimization. It's also convex, and again, this huge number of constraints on the negative class is replaced by one single condition. That's it. Okay? So all that remains are some technicalities. Okay, this is how it looks when you really write the whole thing. So again, exactly the same condition, the maximum margin. The constraint on the positives, here the xj, okay? Xj are the positive. So you want your maximum margin, you want your positive to be accepted, and again you have this single condition which guarantees that this ugly function, although it's a highly nonlinear function, but you can still approximate, assume that after projection this ugly thing looks like a Gaussian, okay, and you can model the probability of it, of a background image to be accepted. Still just one condition. Of course, I'm cheating a little because computing, especially the covariance, will of course be harder because now it's a kernel, okay? But it still can be done, okay? And then we have to answer the question which I mentioned before of choosing your SI. Remember that the SI determine the shape of the kernel. Fortunately, this work was done in a paper by Smola and Sholkov quite a few years ago. And what they ask basically is the following question. Look at all the functions, okay, which are indexed by S, okay? So think about this as a function corresponding to S, which operates on all possible images. So you have a very, very big space of functions. And suppose you want to find a basis. You cannot, of course, hope to find a basis like in linear algebra 101, which will span it. But you can hope to find a basis which will approximate it, okay? So what you want to do is the following. You want to find a bunch of SIs such that every function, like this, if you look at it as a function of x, can be well approximated by a linear combination of k si x. Am I making sense? Remember, of course, that the k's are nonlinear. This is, of course, what makes it a difficult problem. Okay? And these are a natural choice to use for our classifier. So, as I said, fortunately, they have a very efficient, very nice, very clever, very quick algorithm to find such a set of SI, and we use them. And here there's something which is sort of interesting. If you look at the number of SIs that you need to approximate the entire space of functions, you would expect it maybe, if you would think about it 2 seconds, then probably many of us will assume that the number would increase with the number of categories. The more categories, the more images, the bigger the function space, and you would expect that if you have this approximating subspace of functions, you would expect the dimension to increase. However, it does not. It increases in the beginning, then it sharply drops with the number of categories, and it stabilizes around this. This is not really a new result. People have noticed this for other problems like the PCA dimension. And probably what happens is that while adding more categories increases the number of functions that you have to approximate, but you also find really good ones here and there. So here and there you're lucky, and you added these categories, and you find some really, really good spanning vectors in them. So fortunately, from the computational point of view, this number does not explode, does not increase, and eventually it means that the classifier will be relatively small, okay? It will not contain, as you must know, if you don't do any computational tricks to reduce the number of support vectors, and there's a great deal of work on that, but still, you can easily run into situations, I mean, people run these complicated systems, and they have many, many thousands of support vectors. We will have a much smaller number, okay? Less than 100. Okay, so that means that not only the training, but the classification itself is relatively fast. Okay, so we choose a bunch of SI, basis function, using this trick by Smola and Sholkov. And then what we do something very simple. When we build a classifier, it turned out that this by itself works reasonably well, but still, it turned out that if you want to classify, for example, the class of a bicycle, okay, it turned out to be better to also add, okay, to throw in all the positive samples that you have. Okay? So we have these, which are common to all the classifiers, I mean to the classifiers of all categories. Okay, and they are computed just once. You can have 10,000 categories, doesn't matter, you compute them only once. But then when we build the classifier for bicycle, we throw these guys in. Okay, that kind of makes sense, right? I mean, if you're going to classify bicycle, probably it's a good idea to add them in there. It does complicate things computationally a little, but it's not really bad because the big problem is to determine this set. And we don't have that problem here because we simply add all of them. Because usually, as you know, in these problems, the size of the positive sample set is very small. 30, 40, 50, something like that. Okay. And then we simply run the whole thing. We run the optimization. And now there's a lot of ugly stuff on computational efficiency. But I think that I will simply spare you that, okay? Because basically what I hopefully convinced you is that for the linear case is clear, it's very simple. For the kernel, okay, it's also much more, the training is much more efficient because we don't have to deal with this huge set of negative examples, okay? And we don't get this result with thousands and thousands of support vectors, most of which, of course, come from the negative set, because that's the largest one, okay? So the number, by the way, I call them support vectors. It's obviously some slight abuse of terminology. I mean the images which constitute the kernel, okay? And the number is, like I said, typically not more than 100. So everything runs pretty fast. You have to estimate the covariance. This part of the covariance, which is composed of the common SI, you compute only once. These you compute for every category, simply empirically. And that's basically it. Okay, I'm skipping over this because it's kind of boring technical stuff, but I hope you can tell me if I'm wrong, that I convince you that computationally, it's a much, much simpler problem. Okay, so have I convinced you? Okay, nobody's protesting, so okay. And again, the number of parameters you have to find is much, much smaller, okay, because you don't have, okay, if you have n negative examples, or it doesn't matter what you use, I'm sorry, for training. If you have n positive examples from every category and C is the number of categories, then for standard SVM, you have C times n vectors and constraints to handle, but here we don't. Here, it does not depend on the number of categories, okay? It's fixed, okay? So the kernel case turns out to be not really fundamentally different from the linear case. And there are some results. Okay, these are the databases. I have to confess that I don't program, so Rita and the graduate student, of course, did all the programming, but you must be aware of these databases. I will really skip this. And the most important thing, the results. The results were pretty decent, so it actually performed on par with kernel SVM. Okay, and for some reason, which we are not even sure, for the linear case, it does quite better than linear SVM. And hopefully we don't have a bug in the linear SVM implementation. It was a bit intriguing for us, but anyway, for the kernel, it did pretty good. This is the distribution of the probability the probability of having a background image fall in the acceptance region, and as you can see, it's pretty small, okay? These are different dots correspond to different classes, because every class has a different classifier. So, for example, this tells you that if this was, I don't know, class number 5, then the probability of the background to be accepted was 0.02 or something like that. Okay? And here we have a table which compares the resources that we need in terms of memory and optimization. And when it works well. There's a clear advantage in terms of training time, detection time, and especially optimization. Okay? Because, as I said, again, apologize for repeating myself, but this is an important point, that it does not depend on the number of classes. Okay? You can have a zillion classes, but when you train a classifier for each class, the number of constraints and parameters is fixed. It does not depend on the number of classes. Okay? So it worked pretty well, and that's basically it. So the main idea is very straightforward. You replace the negative samples with a distribution. You look at the negative set as a background class, and you treat it like some prior distribution over all images. And there's this hybrid classifier, okay, which means that you're separating not positive samples from negative samples, but positive samples from this prior. And once you write it down, then you get only one constraint, which replaces this entire huge set of constraints on the negative examples. Like I said, this estimate of the background probability is done only once. And the performance was reasonably well in terms that it's much faster. And in terms of classification, it does as well as plain old kernel SVM. Okay? And now we have various ideas for extending this. For example, looking for more complicated classifiers, using a few classifiers simultaneously. But this is work in progress. So thank you very much, and I'll be happy to, any questions, comments, I'll be happy to hear. Thank you.
Thank you for your very interesting talk.
Thank you.
So the background modeling is definitely very interesting and very important. But at the same time, don't you think it's a little bit restrictive to look at classifiers where you do one versus the rest?
You're definitely correct, and we are disturbed by this, and we are looking also at ways to do, not one versus all, but to identify the class given. And what we're doing now, and it seems to work well, but we didn't have enough time to do it, is do something which is the same idea that they do in SVM, because this does give you, after the smoke is settled and you solve this optimization problem, you still get a separating hyperplane. And you can look, for example, at the score that you get for every class and choose the one which maximizes. Yes. So yeah, you're right, and we know that it's more interesting to the community to do this. I mean, not just separate this from this. I give an image, tell me what it is, and we're definitely working on that. Yes, yes, yeah. We got a lot of heat from the reviewers on that, so we're definitely aware of that. Yeah, it's important to do.
Well, perhaps, Antonio, you could suggest a multitask classifier, which is very powerful and very challenging to analyze, and could perhaps benefit from some, strong mathematical minds being brought to it.
That's the.
Don't look at me.
Random forest. Very interesting.
Yes.
You said early on that empirically your projection distributions have heavier tails than Gaussians, but using a model like that doesn't work. So does it not work in the sense that you can't derive the subsequent constraints, or does it not work in the sense
we can write? We tried all kinds of one-sided geometric distributions which look like that, because again nobody knows the real distribution. And we programmed and we optimized and we did everything. It just did not, much to our frustration, I have to say, it did not improve results beyond the Gaussian. So I don't know why this happens. Maybe the way we optimize is not good. I have no idea. We're really very annoyed by that because we really wanted to use, more interesting distributions. Sometimes life is annoying. We're not sure why this happened. No. Yes?
Is there any way to visualize what your standard values look like, even if it is I'm just wondering if you have a representation of what is background in some form. Is there any way to sort of see that? Like, you had the anti-faces. Yeah. Which is actually quite interesting. I'm wondering if there's a way to visualize what anti-something looks like, or, not background.
Well, here we don't use an anti-something in the sense, I mean, there the anti-faces are orthogonal to your image and are smooth. Here, it's a good question, actually. I mean, how does this background assumption affect the shape of the W, right?
In fact, you can see that there's a connection there quite easily, right? Here's the Gaussian blob in the center.
Yes.
My hyperplane almost certainly can't go through the center.
Right.
It must be a chord.
Right.
And that chord is essentially normal to that plane is normal
to
the
Yes, which is the same as happens in antifaces. Yeah. But it means that the difference between antifaces and that is not that much in the background, but in your positive class. And the antifaces, it's very simple. It throws the entire positive class almost to the origin. That's it, because they are orthogonal. But it does actually give you, when you multiply your W's with a background, it actually gives you, like Andrew said, a very wide distribution. So that means that probably it's not very easy to see how it looks. Okay? If you look at if we would look for something which is orthogonal to the background, then it would have some very definite shape. But both here and in antifaces, it's different, okay? Because when you multiply it with 1,000,000 images of the background, the results will not be concentrated. They will be very wide. So what exactly it means that it's not orthogonal to the direction of whatever direction there is, to the set of images. So I cannot...
I mean, and it's obviously a multi-dimensional thing, which would be very hard to represent. I ask because in your core problem that you described, it was given a photograph, which object is in it, or like which class?
Yes.
Or, is it in this class? Which is, it seems, is from the problem of where we had lots of cameras all over the world and different spots, and we were trying to tell, is there a car, is there a person in that? I'm wondering, as the image processing problem goes more towards the mobile space, where you can aim the camera at things. That there might be I can aim it like at a chair and say, oh, what is that? And in some ways, then if the image is actually targeted and it's not saying, oh, find me, is this object in this photo anywhere, but like, what am I primarily looking at?
Yes.
It's, with that, then it would actually be more meaningful to have like, what does the background look like? So it's just a different way to phrase it. Like if you think about the being a search problem, it's much more what looks like this thing. It's not as such is a known class in the given image.
Yeah.
So
Well, your question is a very good one. We actually chose the coward's way out because we don't ask how the positive look. The positive are given, and we only model the background. And the background would be the same. It doesn't matter how you look, where you look. We assume that the background is this huge, very complicated prior. We don't even try to model it. We only try to model its one-dimensional projections, either by linear or nonlinear functions. So we don't really deal with the appearance of the positive class, assuming I understood the question. And if I didn't, we can talk later.
Oh, no,
But, yeah.
Can I just ask one question for the video?
Yeah.
People must have talked about comparisons to LDA. Your within
Yes,
class
yes,
variants
yes,
and
yes.
the cross class variants are
Yes.
represented in here.
Exactly. Yes. Yes.
Um,
Well, the idea is not exactly the same. Our approach is different, but there is definitely a resemblance to this 2012 paper, which we spoke about. And I mean, I assume that you meant that paper, not just LDA.
I mean,
Ah,
plain
okay.
LDA, right?
Yeah.
The within class or cross class covariance matrix is your covariance.
Yes, yes, but no.
If you square your constraint.
Yes, but it's not exactly the same in the sense that we don't really try to narrow, for example, the projection of the background. That's actually very, very wide. So in that regard, it's not exactly like LDA. Okay, but I saw that you're referring to the other paper I mentioned by Malik Deva and Hariharan, in the sense that they also use the prior. But as far as I remember, they didn't do it for a kernel, and the approach is a bit different. But yeah, there is definitely a similarity in the underlying idea. I agree. Yes.
Okay, cool.
Okay.
Well, thank you again.
Thank you.